go ahead and get started. Okay, so quick announcements as usual. Just a reminder that although homework B1 was previously due, I think a couple days ago, I've got this grace period of 5 days. I think there's an echo. Let me take care of that. Okay, so there's this grace period of about 5 days. So basically, you can turn it in without any penalty up until I think September 10th at 11:59. And then on September 11th, then the solution set will become available and you can't turn it in after that. So there's no drop policy on the homeworks. There's only like 5 homeworks. So this is kind of a compromise. I give you the due date when I'm kind of expecting it to be due. And then I give you usually about like a 4-day grace period. So if you haven't turned it in yet, you still are working on the bonus or something like that, there's still time. Canvas will have automatically given you a 0 as the due date passed. But once you upload your submission, then it'll go to an ungraded submission and then it'll get graded and the 0 will be replaced. So if you haven't turned it in, there's still an opportunity for that. The ICAs are available. There's an ICA D1 that's coming up before lecture D1. And homework C2 is out and available if you'd like to start on it. It's you technically will have all of the information you need to work on it after next lecture, lecture C2. But if you want to get working on it ahead of time, you can go ahead and do that. Those are 2 questions that are pretty much almost plug and chug out of the book. So it should be pretty easy to start work ahead if you'd like to. As I've mentioned before, Rockwell Arena competition is an option for your final project. If you're interested in that, arena availability, you can check out Canvas for details. Other competitions based on other programs, including FlexSim and Simio, are also options. So I'll probably just keep reminding you of that till the end of September, because that's when the registrations are due for these things. All right, any questions about the administrative stuff? I understand that the lab TA was sick yesterday and had to do Zoom only. So hopefully he'll be on the mend and back and ready to be in person again as soon as possible. A lot of that going around. I also had another student in my lab that was out sick. Okay, so in that case, last time we did this kind of spreadsheet thing so that you could do the example. Just kind of talked about for a single, so this is Kendall's notation for when you take 470, you'll learn about Kendall's notation. And these are, I mentioned that you can build in a lot of different systems that you can build up networks of queuing nodes, and then the nodes themselves, you characterize them by effectively their input model, their service model, and how many servers there are. So this MM1, the M basically, for reasons that we'll discuss later in the class, means exponentially distributed intervals, exponentially distributed service times, and 1 server. So this is a single channel, single server queue. So the sort of the simplest example of a queuing node. And so the idea is our customers are the entities who arrive. There's only 1 customer can be served at a time, and any other customers waiting to be served have to sit and wait in the queue. And so we've learned how to hand simulate that. And so last time we went through the process of how would you simulate that using a spreadsheet. So I stepped through the abstract sort of specifications for the formulas you would use as you populate through those columns. And then this that you get here, which effectively just means you're going to fill in formulas for the first 2 rows and then fill down, allows you to do all the work of that hand simulation for an arbitrary length number of customers. So it's a great way to check your work. Just gives you an example of how by modeling the relationships over time, then a simple spreadsheet can end up simulating these trajectories. So that's what we got out of last time there. And we could show that if you've got your hand simulation output and your spreadsheet output, like this is your first part or the second part of the homework, and this is the bonus of the homework, then we know that we can look in and check our work to see if those things are working. So we can see that customer 3 departed at time 13. So we go down here, customer 3 departed at time 13, that worked. Also see that customer 3 arrived at time 6, departed at time 13. And so if we look at the departure event for customer 3, we can see that 7 seconds were added to the S counter here. So that means that the customer spent 7 seconds in. Well, if we look down here, we can see that customer 3 arrived at 6, departed at 13, 13 minus 6, give us the 7. So there's a bunch of different ways we can check to see that these two tables match. And so you can get all of this output from this down here. So it's another way to calculate that. So that's all that we kind of handled last time. And that brings us sort of to the end of that homework. And so given that there are a couple of days left on the homework, any questions about any of that, the hand simulation or the bonus? Pretty clear what you need to do for that homework B1 if you haven't already done it. Let me make sure any questions online. Okay. All right, so today then, we want to sort of transition from that into the type of Monte Carlo stuff that you'll be doing in lab 3. And so Monte Carlo simulations are kind of a very basic form of stochastic simulation. They're a static form of stochastic simulation. So it's good for you to know about it before we can move on to the dynamic forms. And so lab 4, where we deal with agent-based modeling, will sort of be your first kind of real dynamical simulation. And then lab 5, which we actually get into arena and start doing DES simulations. So I mentioned just now that we can easily do an MM1, that's with one server here. We can also expand that to think about a so-called MM2. So this just means exponentially distributed inter-arrival times, exponentially distributed service times, and 2 servers instead of 1. So there's 1 queue, but then there's some dispatching policy where customers waiting here, if both are empty, they go to A, otherwise they go to whoever's free, otherwise they wait in the queue. And that's a so-called MM2 queuing node. And so we can also simulate that. So this is an example that I took out of the textbook here, where we're going to call one server Able, the other server Baker, and it has the simple policy that if both are free, then Able goes first and then Baker. And so this is a relatively simple change to the diagram, at least. We just added another server. So how much effort do we have to go into changing the simulation logic if we're going to be stuck with a spreadsheet? So let's take a look at that to kind of compare. So this is setting up the spreadsheet for the same problem, but now with 2 servers instead of 1. So if I look down here, I've got my callers, we can do those kind of customers, the inter-arrival times, and then the service times for each one of those customers. And I assume that everybody starts idle at time 0 when caller 1 enters the system. So the question here is, how do we go through and simulate that, and how different does it look? And so we do the same sort of things. So some of the things are identical. So if we know all the inter-arrival times for the callers or customers, it's easy to calculate the arrival times. It's just the previous arrival time plus the inter-arrival time gives you the next arrival time, and we can go on down through that. We can populate that whole column. That's pretty easy, and it's the same for both. Things get a little more complicated in order to figure out which server is picked for each customer. We have to think about what relationship is going to hold at every time point, and we encode that relationship into the spreadsheet. And so in this case, we know that at every time point, you would only choose Able if the when Able available is less than the when Baker available, and you'd only choose Baker otherwise. So there is going to be a this when server available column. This is going to tell you the next time. So if we were thinking about when caller 1 starts, we can say like when caller 1 would arrive to the system, when is the next time that Able is available and the Baker's available? And if we know that information, then we know that for this caller, we should pick the one who's available earliest. And so that's all this is saying here, is that this caller comes in, it looks and it says who's available next, and you just take the next one who's available. And this less than or equal to is going to enforce the if they're both available, take Able. And that's that sets up that, and that's going to be really important for the rest of the logic. So then we have to figure out when does the service begin? Well, what we have to figure out here is which server did they go into. And so this last thing here, this is like a visualization of this min right here. So this is actually going to say that if we know the time when Able and Baker are both available, if we take the minimum across these two entries in this row, that will tell us the next time that service can begin for this customer. And so if we know when the customer arrived, then we'd say, when does their service begin? Well, their service either begins right when they arrive, or they have to wait. And so we're going to take the maximum of these two, because saying that if the next time any server is available is after when the customer or caller arrived, then you have to wait for the server to become available. Otherwise, you just immediately start service. And that's what is encoded here in this time service begins next here. This time service begins here, this column here. So it's not that different than what we did for the MM1 case, but we just had to add this little peculiarity of keeping track of when the next server was available. And the same sort of thing goes on here. So we can say, well, how do we figure out when this server is completion time? Well, it's just going to be whenever the service begins plus the service time if we're in that server. If we're not in that server, we just copy it down. So that's all it's saying here, is that if we're dealing with a caller who's in Baker, then Able's completion time is just going to pass straight down. So that's why it says 4477. They're pretty much doubled, because they're kind of going to go back and forth between who gets which caller. And then it's also going to be flipped the other way for Baker. So with Baker, if we're in a caller for which Able was chosen, like this one, then we're just going to copy Baker's next completion time down. Otherwise, if we are with a caller who actually is processed in Baker, then we need to see, when did the service begin? How much time did that customer or caller need? Add those two together, and then that is when the service is finally going to end for Baker. So again, this like choose logic is a little bit different from our previous example, but once we deal with that, it's pretty much just like the MM1 case. So now we know that when they're going to complete their service, we can now go back and populate when they'll be available, because Able will be available when Able completed its last service. Baker will be available when Baker completed its last service. And that sort of is all the really hard stuff. The rest is pretty much just stats. And so for this caller, we subtract their time service begins minus their arrival time to figure out how long they waited. See, a lot of callers don't wait at all. A few of them have to wait in line. Then we can also calculate their time in the system. And this is another one of those ones where because completion time is conditioned on which server they're in, we have to say, well, this caller was with Able, so I have to look at Able's completion time. Then that's the end time minus the arrival time, which gives us the time in system. So it's not that much different, but what I'm trying to get at here is this is going to become, with that minor modification of the MM1, just adding another server, it starts getting a little ugly to make that change. Like, the logic is all there. It sort of qualitatively matches what we'd had for the MM1, but there's a lot of this if Able, if Baker, like it just gets, the bookkeeping is a lot more complex, which is one of the reasons why as we build networks and networks and networks of these things, we probably, even though we could do a simple MM1 queue in a spreadsheet, the spreadsheet's going to limit us if we want to scale up to a lot more complexity, is what I'm trying to get at here. All right, but before I kind of go on with that, are there any questions about this basic idea of looking for relationships across time? That if you actually did want to simulate a discrete event system simulation in a spreadsheet, rather than thinking in terms of the state of the system at any clock tick, like you do in hand simulation, you look for these relationships that exist across time at every time point. And that's what you encode in the spreadsheet. So I just want to make sure you can parse this sort of thing. This, again, for complex simulations, you will not likely do them in a spreadsheet unless your stakeholder really requires that, because that's a tool that they want to be able to use in-house, and that's the tool that they're trained on, which actually does happen a lot. Okay, so pretty clear on these relationships. Okay. All right, so like I said, we can do it inside a spreadsheet. Like I said, there are certain sponsors, like there are government agencies where, due to regulations, there are only certain software packages that they're allowed to use. Like you might have learned R to do all your statistics in college or something like that. But then you find out that due to a number of reasons, maybe some of them that actually have to do with safety and security, maybe some of them having to do with politics, you can only use SPSS with a certain government job. Or, some, like I have a lot of colleagues who work with the NIH, and they seriously do like almost everything inside spreadsheets. So communicating with them usually means giving them a deliverable that is like a spreadsheet. DHS, I have a bunch of colleagues who work with DHS, Department of Homeland Security, and Visual Basic for applications is like their primary way that they do data analysis, because that's pretty much all they're allowed to do, because they've sort of been spec'd out that they're limited in some of the technologies they can use because it's Homeland Security. So they kind of move at a slower pace because they have to favor things that they already kind of spec'd out and understand how they work. So sometimes you're stuck with this kind of what might seem sort of an archaic way to do things. Now, but like I'm kind of hinting at here, if you make a small change, like going from one server to two, it can require a really significant change in this simple spreadsheet. And so ideally, we would like to move into tools like Arena that would make this particular change in Arena takes maybe a couple of mouse clicks and then you're done, as opposed to rewriting the entire spreadsheet. So, but today I want to sort of, before we build up to there, it's going to give a couple of other examples that are stochastic modeling examples that we can at least capture in a spreadsheet to give you a basic idea of, there's still a lot of power. There's a lot of different application spaces where you can still do a lot with a simple tool like a spreadsheet. Before, after this kind of lecture, we give them up and kind of leave them behind and start going on to the dedicated sim tools like NetLogo, Arena, etc. So that's where we're going. So any questions about this? And that's why in lab 3, you'll probably be doing most of that Monte Carlo stuff in a spreadsheet as well. It doesn't have to be Excel, could be Google Sheets or whatever. But you'll be at least doing the sims in the spreadsheet as opposed to just the data analysis. Okay. All right, so first set of systems that I want to kind of expose you to here are inventory management system problems. So these are very common problems. They generalize to a wide range of different application spaces, just checking online. And so, for example, in most of these inventory management problems, we're simulating events that occur. Okay, so I'd say events usually occur at non-random intervals, but in most inventory management problems, we actually simulate things that happen at regular intervals. So normally, we're thinking about, what's the inventory, what demand is needed each day, each hour, each minute. So we don't care so much about delays, like someone arrives randomly, and because they arrive while someone else is being serviced, they have to wait. It's more about, we know that there's going to be something that arrives every minute, but we don't know how many of those things are going to arrive each one of those minutes, and how do we deal with that? So the muffin baking simulation in lab 2 is an example of an inventory management problem. So what's the inventory there? Well, you can actually think of the empty muffin space as the inventory and the arriving muffins as the demand. So just like if someone arrives to Best Buy and they want to buy 3 refrigerators and they only have 2 in there, and so they have to wait on that 3rd refrigerator, it's the same sort of thing, that if 30 muffins arrive, but there's only space for 20 of them in the oven, then the oven space itself is like an inventory. And the muffins that don't get matched into the oven have to wait for the inventory to become available. So when you see this pattern of regular arrivals with random amounts per arrival, your head should go into an inventory management model perspective, even if it doesn't seem like inventory. Like, it doesn't seem like empty space would be inventory. If anything, we're usually taught, like in a warehouse, the warehouse we don't think of as inventory. We think about the things we put in the warehouse are inventory. But it's still, the problem that you handled in the muffin sim was effectively an inventory management problem. How do I deal with, do I have enough muffin space to account for these muffins that have to arrive and get baked? So So in the key, again, feature there, regular arrivals, random numbers of arrivals at those regular spacing. So generally, inventory carries over from period to period. So the idea would be if you had 10 muffins that didn't get baked in period 1, you got to bake them in period 2. But a lot of times, it's rather than dealing with that complication of all the carryover, we just cost out the unmet demand. And so what we could say is if the 10 muffins didn't get baked, they're going to spoil and we have to throw them away. So we can now put a cost to discarded muffins. And so now instead of minimizing something over many, many days, we might minimize a cost accumulated. So we run one day, we see how much was left over. That goes into a bookkeeping as a cost. We run another day, we see what it costs. So that's another thing we can do with inventory models is that instead of carrying over inventory from one day to another, just wipe out the inventory at the end of each period and cost it. And so, so that's an approach that we're going to see here. So the systems here that we're going to talk about here are going to have things, states like inventory level, and they're often going to require dynamic simulation models. And I think I've got examples of that. So like this example that we'll see a couple of times this semester is something along these lines where you've got time going on this axis here. You've got an inventory level, which is this dark line. And you've got these regular intervals where you check your inventory. And so the fundamental question here is, how often do I check my inventory? And when I check my inventory, if it's low, what defines low and how many more do I order to restock my inventory? And that's what's kind of being shown in this trace here, is that there was an inventory check here, you ordered up to M, then in between checks, the inventory got depleted because people bought things or it was just consumed, and you keep doing that. And so then the question is, well, maybe I need to check my inventory more often, maybe I need to order more per inventory check. So those would be important things that, decision variables we have to worry about there. And for input, our random inputs for our input models would be things like the demand. So how much do people need to use of this resource every day? And that could be random. And then the lead time, after I make an order, how long does it take for the order to actually arrive and restock the inventory? And that could be random. Some days it comes next day, other orders it might come 5 days later. And I might need to account for that in my decisions. So the book talks about this particular problem with refrigerator sales. And this is also very similar to the little s, big S, the SS inventory problem that you'll do in Lab 7. So in this problem, we've got inventory as our state variable that we're monitoring throughout the whole sim, and it's changing over time. Every N days, we order up N refrigerators to bring inventory to M units, like I showed in that picture there. The orders take several days to arrive, but the actual lead time is random. Each day, there's customers come and buy a certain amount of refrigerators, and that also is random. And a lack of inventory leads to back orders or lost sales. So that will be something that we can put as a cost that we don't want to accumulate. However, having too much inventory is also costly. So every day a refrigerator sits in the store, we can get a cost per refrigerator for holding that refrigerator. And every time we go into the negative and have to do a back order, we can also put a cost on that. And so we want to say, how do we adjust M, the number we order up to, and N, how often we order, so that we reduce, for example, the frequency of back orders or lost sales. So those would be the type of things that we want to do here. So how would we simulate that? Well, the two random things I just talked about were lead time and demand. And so this is a probability mass function for demand. So we can say that for each day, you either, this is how many refrigerators do people order. So each day they order 0 through 4. There's a probability mass for each one of those outcomes. So 10% of the days, no refrigerators, 25% of the days, one refrigerator, and so on. For reasons that we'll see later when we start simulating these things, that gets converted into a cumulative probability, and that'll actually make it easier to simulate. And then down here for lead time, we could say that after you order refrigerators to restock inventory, they either come the next day, 2 days later, or 3 days later. 60% of the time it's next day, 30% 20 day or 2 days, and then 10% of the time they're real late and they're 3 days later. And so we got, those are our two random variables there. Those are our two input models. And so if you change the demand distribution significantly or the lead time distribution significantly, even if all the formulas in your spreadsheet stay the same, you might get a totally different answer. That's why these are input models. They're the inputs to our decision. That's why we really have to get these things right. So we take all of that and we can put it into a spreadsheet. And I know it's going to be small to read these things through here, but I'm not going to go through the formulas of what they did here, but basically to give an overview, they simulated 25 days, and each day they could simulate how much was in the beginning of, at the start of that day, what the inventory was, what the demand drawn from that distribution was that day, and at the end of the day, what the inventory was. They can calculate if there's any shortages and penalize those. And then whatever logic they're using to do the order up to based on the M and the N, then they can say whether they put in an order, and then they can draw a lead time to say how long does it take for that order to happen and how many more days are left. And that's why when these lead times, like it says 2, and then it kind of counts down. And whenever it finally counts down to 0, then the inventory jumps up to whatever amount was added. And so with that, they're able to simulate a 25-day period. So this is one 25-day simulation run. So you could say over a 25-day period, how many days did we go into back order? How much extra inventory did we have? It's like we never went to back order. And then you can run that 100 times. So each simulation is 25 days. And then you can calculate from each simulation, this is the frequency distribution for average daily ending inventory of the refrigerators. And so across each 25-day simulation run, we can look at the ending inventory, and down here it calculates an average. And so they're saying that on average, we had 2.6 refrigerators per day at the end of the day in this run. But in another run, and by another run, I mean another set of demands and another set of lead times, all drawn from the same distribution, but just drawn again, so you got different numbers, just like you roll die again, you get different numbers out of the die. If I do that 100 times, just like rolling a die 100 times, I'm going to get 100 different average ending daily inventories, and it forms a distribution. And so this distribution to me might be more useful than just a single average. This sort of shows me that that I can kind of estimate that I'll probably never have more than 6 refrigerators in my inventory, and I'll probably never have less than 1 on average in the inventory. So things are kind of pretty tight here. So that gives me an idea about whether I need to evaluate a change of this M or this N. And so for different levels of M and N, we'll get different distributions out, and we can evaluate whether this distribution meets our performance needs. And that's kind of the goal here. And I'll show another example of that where it'll be a little bit clearer, where we've got sort of a performance threshold that we're trying to hit, and we're trying to minimize downside risk. So any questions about this basic idea, this inventory management sim here, that we ran it for 25 days, took an average across those days, and then we ran it for 100 batches of those 25 days and took a distribution of those averages. And this gives us a characterization of this particular set of whatever the M and the N were here. Let's say the N was 4 days and the M was 10 refrigerators. So we could change M and N and we get different distributions out. So questions about that? It's pretty clear, that particular inventory management problem. Okay. All right, so the other kind of classic inventory management problem that you'll see in a lot of different operations research texts is the so-called newsvendor problem, or the single period perishable problem. So in that previous case, I cared about inventory across 25 days. And so the inventory that was left over at day 1 would go to day 2. And that would help whatever inventory challenges I have in day 2 and so on and so forth. I would have to look across all 25 days. Now, there are some products where you can't carry over from day to day. And a newspaper is one of those. If you don't sell enough newspapers on Monday, you can't resell them on Tuesday because it's old news. It's immediately, not valuable. It's a very perishable product. And so you could also argue that there are some maybe produce things that could be bottled this way. If you don't sell a head of lettuce one week, maybe you can't resell it the next week. And maybe it has zero value the next week, just like a newspaper has zero value the day after. So we have uncertain demand. We don't know how many heads of lettuce are going to be sold each week. We don't know how many newspapers are going to be bought each day. Fixed prices. So we know that every newspaper is $1 or whatever, and a perishable product. We know that if we don't sell them in the one period, we can't sell them in the next period. So that is the news vendor problem, the news vendor model, or the so-called single period model or perishable model. And so, yeah, question?
Would it be possible to then add on a certain supply to this model as well? So we're kind of lettuce example, if you cannot reliably produce heads of lettuce, or if there are going to be companies that suddenly have enough chicken supply, then you add that to this model as well.
So the question of, can you add certain embellishments to this model? And as we'll see, with SIM, it's easier to add those embellishments. These particular simplifications were added so that you could build a mathematical framework that allows you to give you a concrete answer to the problem subject to these simplifications. So once you start adding that, it makes it harder to do the math. So if we stick with a simple example, then you go into a course like 470, and the lazy way to do this is to say, I would like to, for example, maximize my profit for an inventory, for a news vendor problem. And so I can do that by maximizing the difference between the average sales minus basically the loss. So if I look here, like this is my sale price, which is constant, I know it. I've got a every day demand is random, and I've got a certain inventory here. So it's my inventory is my decision variable, my demand is a random variable, but it's going to be averaged out by this expectation. So this is saying that per day, we basically say you're either going to sell all of your inventory or however many papers that someone asks for. You can't sell more than your inventory, and you can't, and you're not going to sell less than the demand. And so this tells me per day how many papers I'm going to sell. Multiply that by sales price, but demand is random. So the 470 way of doing things is to say, okay, well, I'm going to use my probability theory, and I am going to figure out the distribution of this thing inside the expectation, and then I'll take the expectation of that just to get an average. And so mathematically, I can figure out what that thing is there, and then I can subtract off how much it costs to actually buy that amount of inventory. So if I buy 20 papers, this is how much I spend at the beginning of the day. This is how much I make at the end of the day. Gesundheit, and I'd like to maximize that profit. And it turns out that under mild assumptions on the shape of this demand function, you can actually derive a nice mathematical function for this expectation and do a little calculus. You can take a partial derivative of this thing with respect to inventory, set that thing equal to 0, and you actually get a solution that tells you concretely for the mean and variance of this demand model, exactly how much inventory you should stock in order to maximize your profit. And that's great, but if we think about it, what if we care about more than just average performance? Or what if we have other embellishments? What if, for example, it's not completely perishable? Maybe Tuesday's newspaper or Tuesday's lettuce can be sold in another market for less. How does that change the answer? That's a lot harder to do with the kind of simplistic 470-like thinking. So that's part of the reason why we can turn to SIM to just run a bunch of simulated examples and see how well it performs in our simulated world. So let's make that slight embellishment and do a SIM of it. So now in our SIM, and this is an example that I took from the book here, but The idea here is that we have a fixed quantity queue of newspapers purchased each day. So that's how much we're liable for. There's a demand that varies each day, just like before. If at the end of the day, the demand is greater than how much we bought, then we had there was missed opportunity. So that's, so we could have sold more. If, on the other hand, demand's less than how many newspapers we bought or brought, then that's wasted production. It's too costly. So my question is, how does the quantity I bring to the news vendor problem, Q, affect my aggregated profit over 20 days? And in this case, I didn't say expected aggregated profit. I just said aggregated profit. I want the distribution of that profit, not just the average. And that distribution will tell me a lot more about how well I'm going to perform than just, like, because there could be some days I'm really bad and some days I'm really good. And the average doesn't tell me about that. So that's what I want to capture in my sim. So what do I do in the sim? Well, again, I look for the inputs. The inputs here are demand. So I have to come up with a distribution, a real world distribution of demand for newspapers. And so in this case, I'm going to say there's 3 types of news day. There's a good news day, a fair news day, and a poor news day. Good news days happen 35% of the time. Fair news days, 45% of the time. Poor news days, 20% of the time. And then what does that mean? Well, then, based on the type of news day, I'm going to have a distribution of demand. So this is a complicated input model here because it had this kind of 2 stages. I had to figure out what type of news day it is. Like, for example, Queen Elizabeth died today. So maybe it's a big news day because a lot of people want to read about the Queen, and the new incoming King, Charles III. But maybe there's other days, like yesterday was kind of a low news day, So those are the types of things where, just knowing the type of news day then sets up possible distribution. So this allows me to say, like, I don't want to say every good news day, 60 papers are always sold. What I want to say is on good news days, it's more likely that 60 papers are sold, but sometimes 20 papers will be sold, sometimes 80 papers will be sold. So that's what we draw, what type of news day it is. And then down here, we say for good news days, here's all of the possible outcomes for papers, 40 through 100, and here's the probabilities that correspond to them. So you can see on a good news day, we've got most of the time, the mode is up here at 80 papers being sold. 35% of the time, 80 papers are sold. On a fair news day, the mode says 60 papers are sold. But notice the distribution spreads around that. It's not always 60 papers. And on a poor news day, most of the time, only 40 newspapers are sold. So I can build that into this model here, and then the corresponding CDFs as well. And so that, it shows we need to get these things right in order to make this model work. But let's assume those are right. Then we go in, and now we can simulate one 20-day simulation run. So we've got days 1 through 20. And if you were to read down through this column, it randomly drew what type of news day that day was, fair, good, poor, etc. And then after it draws what type of news day it is, it looks into that table of demand distributions and it draws how many papers were sold that day or were attempted to be sold that day. And then from that, it can calculate the revenue from sales, the revenue from excess demand, the revenue from scrap, or the salvage from scrap. And so in this case, they're actually saying the newspapers have some salvage values. So they do something with them. They turn them into toilet paper or something at the end of the day, and they at least get something back from them. So they added that complication into the model. And then they can add the daily cost. So that is constant there because we're assuming for a particular, this is 70 newspapers. So this is how much it costs to buy 70 newspapers each day. So after all of that, you can calculate a daily profit. And then so over 20 days, what was my profit? And it's fortunately not in the red. So, so they made money here. So then the question was, if I were to run that 100 times, so this is like 100 different 20-day batches, each one of them has a different set of, so it's the same distribution, but it'll have a different pattern of news days and demands. Then what is my distribution of profit? And I get something that looks like this. It's a histogram here where I've got all my profits down here and the frequencies up here, and it's got this particular shape. And now I can start asking performance questions about this distribution that go way farther than anything I can do in 470. So the idea here is like, if I look at this, for example, the average performance is, let's say, whatever this is, like 150 bucks. So it says on average, every 20 days, you make 150 bucks. Now, let's say that I have a performance threshold that you have to make 100 bucks every 20 days to really, to be worth it, to really pay like the poor news kid on the corner who's saying extra, extra, read all about it. In order to pay that kid's salary, you got to be making at least 100 bucks every 20 days. So that is my minimum performance threshold here. Well, I can see that some of my simulated days fall under that 100-buck performance threshold. So even though on average, it looks better. So you come out of IEE 470, you learn how to do all the average math, and your average math says on average, you're meeting your thresholds. You're on average, you're always going to make, on average, more than 100 bucks. But in reality, I can take these outcomes, divide by the total number of outcomes. Like, let's say these are 10 outcomes down here. So 10 out of 100 outcomes are underperforming, are under my threshold. Well, that means I have a 10% downside risk. So that means this venture, 10% of the time, will fail to pay the salary of the poor kid trying to sell the newspapers. So that's the reason why we like to get distributions out, because we can start asking more interesting questions about performance, like questions like, what is the downside risk? We can set up these thresholds that simply are not captured by knowing just the average alone. So any questions about that? One of the values of these stochastic simulations, we lose the mathematical tractability, but we gain the ability to estimate more complex features like this. Now, it's true that if you ran this experiment again with another 100 replications, it would give you maybe a slight perturbation to this distribution, because it's all random. Like, this might be 145, 129, this might be 140, 134, or something like that. But this is an estimate. And so we are going to learn in the class how to put confidence intervals on our estimates, so that rather than me just saying there's a 10% downside risk, I'll be able to say there's a 10% plus or minus 3% downside risk. So that way they know that it could be as bad as 13% or as good as 7% in terms of my downside risk. All right, so questions about that or comments? Questions online? All right, good. So those are two examples that, inventory management example, and then kind of broken into this kind of dynamic case and this more sort of traditionally static case, but that we can embellish into another dynamic case here. And then the other thing that we want to talk about here is I want to introduce the Monte Carlo method a little bit, which is where your lab 3 is going to take you. So you're going to do a couple of different Monte Carlo examples here. Now, how many people have ever done Monte Carlo simulations in the other classes? Maybe reliability work or anything? This is new. I've done some numerical analysis courses, things like that. People talk about Monte Carlo. So Monte Carlo analysis, so as I think I talked about in the lab video, so this Monte Carlo is a reference to casinos. And the idea was these methods were developed when they were developing the atomic bomb. And at that time, it was highly, these numerical methods were highly kind of classified. So they came up with the code word that would allow them to talk about these methods without giving away what they were talking about. And that's where they came up with this word, Monte Carlo method. And so that's where that kind of comes from. And it's a stochastic approach, which we use random sampling to precisely estimate a quantity that would be impractical to calculate exactly. So it is stochastic modeling, but it's doing it for numerical reasons. And so we'll have kind of examples of that. So this is very similar to an activity you're going to do in lab 3. In lab 3, you are going to draw random numbers and use them to estimate pi. So by now, hopefully in a bunch of math classes, you've learned different ways to estimate pi. You can do Taylor series expansions, or even just measure circumference and diameter and try to get that right and things like that. You can also just randomly throw dots at a chalkboard and see where they land. And if you know how to read those kind of tea leaves there, you can actually then estimate pi. And so you'll learn how to do that in the lab. And this is kind of a similar question here. So if we're analyzing a bombing mission and we've got a bomber, we know it's going to drop 10 bombs, but because of wind and other things, the bombs don't drop straight down. They drop with some distribution. And so the same bomber, if they were sort of sitting at the center of this target, if they drop 10 bombs, those bombs might land in a distribution here for which these 10 points are samples of that distribution. So our question is, what is basically how likely is it that they're going to actually get bombs in the destination area? So we could do complicated math there. Like if we actually know what the distribution looks like, we could do a little contour map and we could do a little integral and we could try to figure out how much area is within just this bombing region. But if this bombing region is sort of ugly shaped, it might be a difficult calculus problem to solve. So instead, we use Monte Carlo sampling. And so what we're going to do instead is we're going to generate every row of a spreadsheet is going to be 10 bombs. In other words, every row is going to be 20 positions, an X and a Y coordinate. So there'll be 10 X's and 10 Y's. And so in each row, I'll know the position of each one of those simulated bombs being dropped. And so the assumption is that I can easily draw from the distribution that each bomb comes from. And then once I have that row, I just do a little geometry to figure out how many of those 10 bombs in that row landed in the area. And it might be just 6. Now, from one row, I can't just assume that 6 out of 10, that means 60% are always going to land in the area. That just could have gotten lucky or unlucky. So I'm going to repeat that experiment over hundreds of rows, and we call those Monte Carlo samples. And then we're going to average how many landed across all of that. And what we can find is on average, maybe there's I've got this distribution here. So frequency distribution, number of hits in 400 bombing missions. So I've got 400 rows, each one of them's got 10 bombs. And so we're saying there are some rows where only 2 of them hit the area. There are some other rows where 10 of them hit the area. But in 113 of the 400 rows, 7 hit the area. So I could take the average over this distribution if that's the right one, or I could do the same for like the downside risk calculation. I might say that this mission is only a success if at least 4 get into the area. So then I could figure out, well, what fraction of these were less than 4? And that's a downside risk calculation. So that's an example of what I could do here. But what I'm really doing is estimating an area using random sampling. So what I would usually do an integral for, I now, by taking an average of this distribution, can get a numerical estimate of. And if I draw more and more rows, the average of this distribution will get closer and closer and closer to the area in that little section. And that's what we'll sort of play with there in lab 3. That's one example of a Monte Carlo simulation. Any questions about that? The general idea that I've got this picture, I like to sort of figure out what's the area inside this funny shape, distribution from one bomb, but because that's complicated to do, I just drop a bunch of these and see how many land in the shape, and then do that a bunch of times, and then take the average. And that's Monte Carlo sampling. Okay. Questions online about that example? And again, you'll have a chance to play with this in a couple of examples in lab 3. All right, so reliability problem. This is another one where you've got like a milling machine and it's got 3 ball bearings. Each one of them could fail at any time. And I can say per ball bearing that there's on average maybe 1,000 hours between every failure. So sometimes it's 800 hours, sometimes it's 1,200, but on average it's 1,000 errors between every failure of the ball bearing. But every time I make a replacement, not only do I have to buy a new ball bearing, but the machine's going to be down during the whole time that I'm waiting for someone to come and fix it, and the time it's actually being fixed. So I've got downtime, and then I also have to pay somebody to fix it. So the question is, and this is why a lot of times you go into office buildings, you'll see that there'll be a couple of burnout bulbs, and it'll be that, and you probably go to classrooms, and you'll notice that there'll be one bulb that's burnt out for the whole semester. And you think, well, did somebody just not ever report it? Like, and the thing is that they make decisions about it, like there's a minimum number of bulbs that has to burn out in a room before they send somebody out to fix them. Because otherwise, they think if the room is still kind of usable, it's much cheaper for them to replace 3 bulbs at once than replace 1 bulb and then another bulb and then another bulb, because there's a huge amount of time just to set up each replacement and cost. And it's the same thing here. It might be that instead of replacing 1 ball bearing, we actually replace all 3, even if the other 2 are still good. And that's kind of the question here, is that how do we replace this? Do we replace 1 at a time and just wait for each one of them to fail? Or do we just replace all 3, knowing the other 2 are probably going to fail coming down the line? So our experiment here, we're going to do in a Monte Carlo simulation, is we're going to simulate 15 free bearing sets for 2 different policies. One policy is to replace each ball bearing when it fails. The other policy is to replace all 3 when any of them fail. And then for each one of those policies, we calculate the useful lifetime. So that corresponds to how much time the machine was actually on over the 45 ball bearing period, and what the repair costs were. And so we can do both of those things. So in a spreadsheet, we randomly draw the lifetime of each one of those 45 ball bearings. And then we also draw the delay until a mechanic arrives for each repair. So that means that if I replace each ball bearing only when it fails, then I'm going to have 45 delays. But if I replace all 3 ball bearings when any one of them fails, then I'm only going to have 15 delays, because every time one fails, we knock out the other 2. And so then the question will be is that I will have for both of these a useful lifetime and a repair cost. If I divide the cost by the provided lifetime, then I get kind of a rate, so I can say for this amount of lifetime, how many costs were accumulated, and I can compare which one of these policies is actually better. So that's an example. This would be very difficult for me to build a mathematical expression for, but it's relatively easy for me to simulate and just compare the 2 strategies. And it's a Monte Carlo simulation because really the experiment is about sort of 1 machine with 3 ball bearings, but we're sort of choosing to run 15 of them and then take the average over that 15 to sort of average out all the noise to give us this rate. So that's kind of an example there. So I want to move on to an example like the one you're going to do in lab, but are there any questions about that kind of example? In other words, the reason it's a Monte Carlo is we're sort of averaging over a bunch of experiments in order to get an estimate of a number, that number being cost by lifetime. If we just did 1 experiment, it would be too noisy. So we do 15 experiments and average over all of them. And that gives us an estimate of the cost to lifetime ratio for both of these policies. Okay. All right, so last example I have here that links directly to your lab is one of these stochastic activity networks. So those of you who already looked at the lab, probably familiar with this already. Those who haven't gotten to that yet, then this will give you a little intro. Imagine this activity that has 3 branches that need to happen for the activity to be completed, and they all happen in parallel. Their example, I think, in the book is breakfast, which is why I've got these things up here. And so the idea is in order to make breakfast, you need to make eggs, toast, and bacon. Eggs has 3 steps, toast has 2 steps, and bacon has 1 step. And so that's modeled down here, where this top branch is eggs, where going from start to A is step 1, A to B is step 2, B to finish is step 3. Toast is 2 steps, start to C, C to finish. Bacon is just this 1 step down here. Now, each one of these lines is labeled with a probability distribution. In this case, it's a uniformly distributed random variable between 2 and 4. So that means that this, in order to get from start to A, it could take you anywhere from 2 minutes to 4 minutes uniformly distributed. If you add up the average here, so this is an average of 3, this is an average of 3, this is an average of 3. So on average, it takes you 9 minutes to get through the top branch. Down here, this is an average of 4.5, this is an average of 4.5. Again, 9 minutes to go through the middle branch. And down here, the average of 6 and 12, well, that's also 9 minutes. So it's 9 minutes on all 3 branches. And so the question is, if we can't call the breakfast done until all 3 branches are completed, then what is the distribution of time it takes to complete the breakfast? Or even what's the average time it takes to complete the breakfast? And it's tempting to say the breakfast will be completed in 9 minutes because all 3 branches are 9 minutes. But what you're going to find is that won't be the case. That when you combine these activities in parallel, they combine in a way so that the average time will be greater than 9 minutes. And we can start thinking about that in terms of what do we think the distribution is across the top branch versus the bottom branch. Now the bottom branch, I said, it's uniformly distributed between 6 and 12. But the top branch is a sum of 3 uniform distributions. Does anybody know of a theorem that would suggest why adding up 3 independent variables would give you something that looks bell-shaped? Central limit theorem. That's right. What is the central limit theorem? Anybody else? Anybody? Like most important theorems in probabilistic modeling. Has to do with adding things up. Or what, yeah. That which is normally distributed? Well, it's this, well, not the mean, but the sum. So if I was to think that, if I'm to add up 3 independently distributed random variables, that's going to give me a sum every time I add them up. That sum has a distribution. The more things you add up, the more bell-shaped it gets. That's the central limit theorem. If you pulled up the carpet right now and looked at the pad underneath it, it would be relatively unworn there, and then it would fade into a worn stripe that would probably be really dark here all the way to that door. And if you took a cross section of that stripe and you were to sort of plot out, how dark it looked, it would form a bell curve. It would form this a shape look like this, sort of a bell curve. And that's because every time someone walks on the carpet, they're walking in a relatively independent way. Like I'm walking, but like the path that I just took up here was independent of the path that I took before that. It's like it had the same average. Like on average, I walk in between these 2 things, but it's independent of that. So they all have a consistent average, but it's not like when I walk to the right, it forces me to walk to the right later. So that independence and kind of a similar average is what is going to cause them to have this wear pattern that is going to be bell-shaped, where it's the strongest in the middle and then fades out after that. If you go to any door in the university and look closely at it, it will have a wear pattern that looks like that. It'll be really dark in one spot, probably in the middle of the door handle, and it fades after that. Anything that has additive wear is going to look bell-shaped when you look at its pattern because of the central limit theorem, or the central limit theorem describes that. Here, we have, this is not a wear process, but it is still an additive process where we're adding the time it takes to make 1 egg, 2 egg, 3. Well, that's not how you make eggs, but there's 3 steps here, right? And so we're adding up 3 independent steps. And even though each step is uniformly distributed, what this curve tells me is that it would be really, really rare for all 3 steps to be at their minimum at the same time. And it'd be really, really rare for all 3 steps to be at their maximum at the same time. And that's the reason why when you add things up, you get something that's bell-shaped. So what that tells me is even though there's uniform distributions everywhere across this thing, because I'm adding them, this top path goes from 6 to 12, but it pretty much hangs around 9, even though this bottom path uniformly represents everything from 6 to 12. So what this is going to tell me is that this top path is going to tend to finish earlier than this bottom path, because it will be rare for this top path to ever take 12, but it's not that uncommon for the bottom path to take that 12. And when I start taking the maximum across all 3 paths here, then what we're going to see is where you might have thought that the top path and middle path and bottom path, whichever one were the maximum, that would probably be, either it would be just sort of luck of the draw, could be all 3 of them. What you actually should see is that you'll get the bottom path will take a lot longer, or will be the longest path more often than the top. So those are the types of results I want you to focus on as you're doing lab 3, is that distributions matter, and they matter a lot. We can't just characterize the world by averages, because on average, these three paths are identical. In reality, the top path is very differently shaped in distribution than the bottom path, and when we combine them together, that difference is going to mean that we don't get sort of an equal usage of all 3 paths, and the distribution of the whole activity is not going to be as you expect. It won't be an average of 9 minutes for the whole activity. So that's kind of just sort of a preview of what I want you to think about as you're looking at the analysis when you do this in lab 3. So are there any questions about that? And also, as you're walking around, the university or anywhere, look for these bell-shaped wear patterns, because they're everywhere. And it's just the central limit theorem. It's like the stars, like in the sky. It's everywhere. Okay. Questions online? Okay. All right, so how are you going to simulate this in a lab? So basically, in each spreadsheet row, you're going to store, if I look back here, there's 6 random variables, 1, 2, 3, 4, 5, 6. You're going to basically draw in every row 6 random variables, 3 from the breakfast system, or 3 from the egg distribution, 2 from the toast distribution, 1 from the bacon distribution. And in each one of those, you'll be able to sum up the 3 short ones, the 2 immediate ones, and then leave the other one alone and ask, which one's longest. And so that will tell you which one is the critical path, but that also will tell you how long it takes to finish breakfast. And so you'll then be able to run stats on the paths, which one's longest, and the distribution of how long it takes to run the breakfast time. And that will be your analysis of this so-called stochastic activity network. So that's what you do in the lab 3. So questions about that? That's one of the things. You'll estimate pi, and then you'll do that. Okay. All right. So so basically, just to wrap up today, spreadsheets can be really useful, as I kind of talked about through the rest of the day here. We can do a lot with them. We can even do things like start characterizing things like downside risk. Like, we can get a lot more interesting, rich performance things out of them. But as the systems that we're going to see, they would be really hard to shoehorn in to a spreadsheet, which is why we have to learn these additional tools, be they NetLogo, Arena, FlexSim, Simio, whatever. Because these tools, although they're a pain to learn at first, they give us the power to draw far more complex systems than a simple spreadsheet would allow us to do. And these even go to something as simple as, a drive-through. If you think about, there's different ways to organize the drive-through lane here. You've got multiple places you can order. Do I put the ordering in sequence? Do I put them in parallel? How does those work? How do I compare those 2 things together? Will my answer vary depending on, whether it's breakfast time or lunchtime, or in between those, the demand distribution? So when we look at even something as simple as a drive-through, there's enough complexity that would be a pain to try to simulate in a custom-built tool that you sort of built on your own. And we like to answer these more complex problems about when do you order ahead? What do you have? How do you deal with these stochastic lead times? How do you deal with some, coffee takes a lot longer to make than maybe heating up a sandwich, which seems weird when I say it that way, but I guess that's just the state of fast food. But all of these different things go into it, and they really add these complexities that using these tools that we feel more comfortable with at first, we have to sort of start saying, you know what, it's worth investing in learning more complex tools, because as you'll see, it's much easier to get sort of more realistic systems into these other tools. So, so we want to, like I said, increasingly difficulty, it's hard to manage on a spreadsheet. So we want to be able to automate tedious repetitive coding required. So we reduce the chances of making mistakes and simplify the process of making structural changes. We're going to have all sorts of tools inside these programs that really allow us to take quick shortcuts. And so in Arena, you've got things like carts and conveyor belts and finite length queues, things that if you were to try to build the equivalent of it in your own programming, like even if you want to write everything in Python, like, you have to do everything yourself. And so much because so many of these problems, inventory management problems that look so similar, that the people who build these tools have already given us sort of a bunch of the code sort of ready for us to run. And they usually have attractive graphical visualization options, which are not only make the programming task sometimes more enjoyable to do, but you can then lean over to a stakeholder and say, rather than me show you a table of data, let me run a sim, and you can actually see people moving around the simulated factory. And that often is a much better communication tool. So I want you to not forget about the communication side of this course. So much about learning these sim tools is about better communicating complex results to your stakeholders. But I don't want you to forget about your stats tools and your spreadsheets and so on. What we'll find is that Arena gives us rudimentary ways to look at the data that comes out of our sims. But it also allows us to dump them into spreadsheets, and then we can actually then analyze them using Excel or using R, SPSS, and so on. So even though it's outside of the scope of this class for me to show you how to use R or SPSS to analyze the data coming out of Arena, if you already feel comfortable with doing that, then certainly, especially for your final project, you want to run a t-test in R, go ahead and do it. That these tools are very complementary to the sim tools. The sim tools really are not for stats. The stats tools really are not for sim. Really, every good industrial engineer uses both simultaneously. What I'm going to get here. So these are the tools that I've been talking about. We're going to focus most of this semester on DES, process-centric. Starting in Lab 4, you'll see agent-based modeling and a brief intro to system dynamics modeling, but it's primarily agent-based modeling here. And that's kind of where we're going. So that's, I think, all that I've got for you. So any questions or comments? Pretty clear where things are headed? Okay. So in that case, let's, I think that's the last one here. So let me put a attendance question up. I'll put it in the chat as well. So the attendance question for today is, so what is the name of the theorem which very well describes additive wear processes in nature? So what is the statistical theorem that very well describes additive wear processes in nature or engineered systems? And like I said, that's all I got for you today. So if you have any other questions, feel free to come up. Otherwise, have a great weekend. Try to stay out of the rain if it comes up, and we'll see you Tuesday. Any other questions online? If not, then I will go ahead and close the room. If I can find my mouse, there it is. Have a good weekend.